Right now, somewhere in a clean room in Pasadena, California, a team of engineers is celebrating. They have photographs of rust-colored soil, photographs of a horizon that curves the wrong way, photographs taken by a machine they built traveling at 19,000 kilometers per hour that they slowed to zero in 7 minutes using a sequence of parachutes, rockets, and a sky crane lowering system that should not, by any reasonable engineering intuition, actually work. They are celebrating arrival. They should not be celebrating. Arrival is not an achievement. Arrival is a controlled fall with good documentation. Every object in the solar system is falling. The planets fall around the sun. The moons fall around the planets. Everything is falling. What we call landing is simply the moment a falling object stops being useful and starts being furniture. Mars has a graveyard. It is not metaphorical. The surface of Mars contains the remains of at least 18 confirmed mission failures: Soviet probes, European landers, American orbiters. They are there right now, partially buried, oxidizing slowly, becoming part of the regolith they were sent to study. Mars does not care. Mars has a surface gravity of 3.72 meters per second squared, a thin carbon dioxide atmosphere at roughly 0.6% of Earth's sea level pressure, and absolutely no interest in our engineering ambitions. We have successfully landed on Mars 9 times. 9! Out of more than 50 total mission attempts. 9 successful landings. That is an 18% surface success rate. We celebrate this. We print commemorative posters. We name the landing sites. But here is the number no one prints on a poster. 0. 0 successful returns. Not 1 gram of Martian material has ever been intentionally recovered and brought to Earth. Not 1 cubic centimeter of atmosphere. Not 1 microbe, confirmed or otherwise. We have sent mass to Mars continuously for decades, and Mars has returned nothing. That is not a mission parameter. That is a thermodynamic statement about the structure of our civilization. The universe has a direction. It flows from order to disorder, from hot to cold, from concentrated energy to diffuse entropy. And in this solar system, for our species at this moment in history, it flows one way, outward and downward, into gravity wells, into the dark. We are very good at sending things away. We have no demonstrated ability to bring them back. This is the autopsy of that asymmetry. Meet Perseverance. Perseverance is a 6-wheeled, nuclear-powered, laser-equipped geological research platform. It weighs approximately 1,025 kilograms. It cost $2.7 billion to build and launch. It drives at a maximum speed of 0.152 kilometers per hour, which means it cannot outrun a human walking slowly. It has been operating in Jezero Crater since February 2021, methodically traversing a landscape that has not experienced liquid water in approximately 3.5 billion years. Its primary mission, the one that justifies every dollar and every engineering hour, is this. It drills small holes in rocks. It seals the extracted material in titanium tubes, approximately the diameter of a cigar and 15 centimeters in length. It then either caches those tubes on the surface or retains them in its interior. Each tube holds a few grams of material: regolith, core samples, atmospheric gases. Perseverance is, functionally, an automated sample mortician. It is preparing a collection of small coffins for a dead world's remains. As of 2024, Perseverance has collected and sealed 24 sample tubes. It has also deposited a cache of 10 tubes at a location called Three Forks as an insurance policy, a backup collection in case the rover itself becomes non-functional before a retrieval system arrives. It is a precaution against the rover dying before it can witness the completion of its own purpose. This is not sentimentality. This is mission architecture. The scientific value of those tubes is not in dispute. The ancient lakebed sediments of Jezero Crater represent the single highest probability location for detecting biosignatures, chemical traces of past life in the accessible solar system. If biology ever existed on Mars, it existed there. If those tubes contain what scientists theorize they contain, they represent the most significant scientific discovery in the history of our species, and they are sitting on the surface of another planet. They have been sitting there for years, and retrieving them requires solving a problem so structurally violent in its energy demands that the primary space agencies of the entire planet working together with a combined budget of tens of billions of dollars have been unable to agree on a viable architecture for accomplishing that. Those tubes exist. The problem is real. The cost is the variable. And the cost is where the physics becomes brutal. Here is the problem, stated with precision. To return 500 grams of Martian surface material to Earth, you do not simply send a probe to pick it up. A probe that descends to the surface and then climbs back to orbit is not a probe, it is a rocket. It is a complete, independent launch vehicle with all the infrastructure that implies. The Mars Ascent Vehicle, the MAV in mission documentation, must accomplish the following: achieve Martian orbit from a standing start on the surface of Mars. Jezero Crater, from rest. Mars has a surface gravity of 3.72 meters per second squared. Its escape velocity to low orbit is approximately 3.55 kilometers per second. Compare this to the Moon, which has a surface gravity of 1.62 meters per second squared and a lunar orbital insertion velocity of roughly 1.68 kilometers per second. The Moon is easier, and it took the Saturn V rocket, the most powerful launch vehicle in human history, 111 meters tall, weighing 2.97 million kilograms fully fueled, to put 12 humans on the lunar surface and bring them home in a module weighing 5,800 kilograms. Mars is not the Moon. The MAV must be compact enough to land on Mars. It must be light enough to be transported from Earth. It must be robust enough to survive entry, descent, and landing, a process that subjects hardware to extreme deceleration forces, thermal gradients, and vibrational loads. It must then survive on the Martian surface for potentially years in temperature swings from -7. Here is the problem, stated with precision. To return 500 grams of Martian surface material to Earth, you do not simply send a probe to pick it up. A probe that descends to the surface and then climbs back to orbit is not a probe, it is a rocket. It is a complete, independent launch vehicle with all the infrastructure that implies. The Mars Ascent Vehicle, the MAV in mission documentation, must accomplish the following: achieve Martian orbit from a standing start on the surface of Mars. Jezero Crater, from rest. Mars has a surface gravity of 3.72 meters per second squared. Its escape velocity to low orbit is approximately 3.55 kilometers per second. Compare this to the Moon, which has a surface gravity of 1.62 meters per second squared and a lunar orbital insertion velocity of roughly 1.68 kilometers per second. The Moon is easier, and it took the Saturn V rocket, the most powerful launch vehicle in human history, 111 meters tall, weighing 2.97 million kilograms fully fueled, to put 12 humans on the lunar surface and bring them home in a module weighing 5,800 kilograms. Mars is not the Moon. The MAV must be compact enough to land on Mars. It must be light enough to be transported from Earth. It must be robust enough to survive entry, descent, and landing, a process that subjects hardware to extreme deceleration forces, thermal gradients, and vibrational loads. It must then survive on the Martian surface for potentially years in temperature swings from -73 degrees Celsius to 20 degrees Celsius in a chemically reactive peroxide-laden atmospheric environment while its propellant remains stable. And then it must launch. This is the mass penalty. Every kilogram of payload you want to return from the Martian surface requires multiple kilograms of propellant to lift it. That propellant requires its own containment mass. The structural systems to hold that propellant require additional mass. The guidance, navigation, and control systems require power, which requires either batteries or solar panels or radioisotope generators, all of which have mass. The mass ratio for Martian ascent, the ratio of total vehicle mass at launch to the dry mass of the vehicle without propellant, must be approximately 4 to 5 to 1 for a viable two-stage solid rocket architecture. This means that for every kilogram of mass the MAV places in Mars orbit, the MAV itself must weigh 4 to 5 times that amount at the moment of ignition. And all of that mass, the entire MAV fully fueled, must arrive at Mars first, which means it must survive interplanetary transit, which means it must survive EDL, entry, descent, and landing, which means the spacecraft that carries it to Mars must be large enough to accommodate it, which means the Earth launch vehicle must be capable of propelling that entire stack onto a Mars transfer trajectory. The mass penalty compounds. It does not add. It multiplies. A rough calculation using the Tsiolkovsky rocket equation, which is not a theory or an estimate, but a physical law derived from conservation of momentum, demonstrates that the energetic cost of returning a single kilogram of material from the Martian surface to Earth orbit is on the order of several hundred times the energetic cost of landing that same kilogram on Mars in the first place. The universe is not symmetric. Falling into a gravity well is cheap. Climbing out of one is expensive. Mars is a deep well. We built a rover to collect rocks from the bottom of that well. The rocks are still there. The Mars Sample Return Mission, as currently architected by NASA and ESA, the European Space Agency, is not a mission. It is a sequence. And sequences have a specific vulnerability that individual missions do not. A single failure in a sequence that requires all components to function is not a setback, it is a termination. State the chain clearly. Step 1. Launch from Earth. Deliver the MAV and the ESA Earth Return Orbiter to separate Mars transfer trajectories on schedule within a launch window that opens every 26 months and tolerates no delays. Any significant technical failure during launch preparation, during launch, or during the interplanetary transit phase results in mission loss. The mass, the engineering hours, the budget allocation, all of it becomes inert matter on a solar orbit that intersects nothing. Step 2. Land the MAV. Execute entry, descent, and landing for a vehicle that cannot be aerodynamically optimized in the same way as Perseverance because it carries propellant, stored energy that is sensitive to thermal and mechanical stress. Land precisely enough to be within operational range of the Perseverance rover, not approximately, precisely. Step 3. Transfer the sample tubes. Either the rover delivers tubes directly to the MAV's sample containment system, or a separate sample retrieval lander deploys fetch helicopters, small rotorcraft like the Ingenuity technology demonstrator, but with a retrieval function that physically collect cached tubes from the Three Forks depot and return them to the lander. These helicopters must function in Martian atmospheric density, navigate rough terrain, locate precisely positioned objects, and return without damage. This step alone, the fetch helicopter component, was later removed from mission architecture during redesign phases due to complexity and cost. The architecture changed multiple times between 2020 and 2024, which is not a sign of design maturation. It is a sign of a mission that does not have a stable solution to its own central problem. Step 4. Launch the MAV from the Martian surface. Ignite propellant that has been sitting on Mars for months or years. Achieve the required delta V. Place the orbiting sample container, the OS, a small sealed canister containing the tubes, into a precise Mars orbit. Step 5. Execute autonomous orbital rendezvous. The Earth return orbiter, which has been waiting in Mars orbit, must locate the OS canister, approach it, and capture it. This is not a docking procedure with a cooperative partner. The OS will not be transmitting a strong beacon. It will be a small metal object in Mars orbit released by a rocket that has no further function. The rendezvous must be conducted autonomously. There is no human pilot. There is no real-time intervention capability from Earth, given signal delay times of between 3 and 22 minutes, depending on planetary alignment. The rendezvous algorithm must work the first time. Step 6. Return the captured sample to Earth. A 2 to 3 year transit. No anomalies permitted that affect the integrity of the Earth entry vehicle, which must deliver the OS canister through Earth's atmosphere and to a designated landing zone, the Utah Test and Training Range in current plans, without rupture, without contamination of the external environment, and without loss of containment. 6 major steps, each with multiple sub-steps, each with its own failure probability. The combined probability of mission success given realistic failure rates at each node is a number that NASA's own internal risk assessments have characterized as presenting significant challenges. That is bureaucratic language. Translated, this is the most technically complex unmanned mission ever attempted, with a chain of dependencies so long that the probability of clean execution approaches a value that engineers are not comfortable stating publicly. A chain is only as strong as its weakest link. This chain has more links than any chain we have ever constructed. In 2020, the Mars sample return mission was estimated to cost approximately $3.8 billion over its full life cycle. By 2023, that estimate had risen to between $8 billion and $11 billion. By early 2024, an independent review board convened by NASA assessed the cost at potentially exceeding $10 billion, with a launch readiness date pushed to no earlier than 2035, a full decade later than initial projections. The IRB used specific language in its assessment. It described the mission as not executable under the existing budget profile, not delayed, not over budget, not executable. NASA's total annual budget is approximately $25 billion. The entire Planetary Science Division, which funds every solar system mission, every Mars probe, every outer planet explorer, every asteroid mission, receives roughly $3 billion per year. The MSR mission, in its revised cost projection, represents multiple years of the entire planetary science budget for one mission to return 500 grams of material. The cost per gram calculation is not a useful metric. It is a rhetorical grenade, and I will deploy it anyway. At a $10 billion mission cost and a 500-gram return yield, the cost per gram of Martian surface material is approximately $20 million per gram. For reference, the current market price of antimatter, the most expensive substance ever produced by human civilization, manufactured in microgram quantities at particle accelerators, is approximately $62.5 trillion per gram. So Martian rocks are not literally the most expensive material ever acquired. But antimatter has a function. It powers theoretical propulsion systems. It serves a purpose in physics research that justifies its production costs as a research instrument. What the Martian rock samples justify is a scientific question that cannot be fully answered until the samples are analyzed. We are spending $10 billion to answer a question we do not yet know the answer to. We are paying the cover charge before we know if the venue exists. This is not irrational. Scientific uncertainty is the entire point of the exercise. You cannot confirm or deny life on Mars without the samples. The samples have potential value that is categorically unbounded. A confirmed biosignature would permanently restructure humanity's understanding of its own significance in the cosmos. But potentially unbounded scientific value is not a line item that fiscal authorities can process. In March 2024, NASA announced it was soliciting alternative architectures for MSR, lower cost options, faster options, simpler options, effectively acknowledging that the existing plan was financially untenable. Multiple proposals were submitted. SpaceX proposed a Starship-based architecture. Various academic and commercial entities proposed simplified concepts. None of these alternatives has been selected. None has been fully costed. None has been approved. The samples remain in Jezero Crater. The mission remains in a state of architectural ambiguity. The budget hemorrhage continues, consuming planning resources and institutional attention, funding a mission that is not yet funded, for a hardware system that does not yet exist, to retrieve material that has already been collected, waiting in tubes on the surface of a planet that has never returned anything to us, and shows no structural incentive to begin. Overcoming gravity in reverse is expensive. Our civilization is currently not willing to pay the price. Assume the mission succeeds. Assume every node in the chain functions. The MAV launches cleanly, the rendezvous executes without error, the Earth-returned vehicle performs nominal re-entry, the OS canister impacts in Utah, intact, unruptured. The samples arrive. They are not opened. They are transported under strict chain of custody protocols to a facility that does not yet exist. As of 2024, the sample receiving facility, the SRF, required to process the returned samples had not been built, had not been fully sited, and had not received construction funding. This is a facility designed to contain, at minimum, Biosafety Level 4 biological hazards. BSL-4 is the highest containment classification used on Earth. It is the designation applied to research involving Ebola virus, Marburg virus, Lassa fever, agents for which no reliable treatment protocols exist, and for which containment failure produces consequences that are considered irreversible at a population scale. The Martian samples will be treated with equivalent containment protocols, not because we know they contain dangerous organisms, not because we have evidence of extant Martian biology, but because we do not know that they do not. The Committee on Space Research, COSPAR, maintains planetary protection policies that classify Mars as a restricted Earth return body. This means that samples returned from Mars are categorized by international scientific consensus as potential biological hazards until demonstrated otherwise through analysis conducted within a contained facility. The science is sound. The precaution is rational. Mars had liquid water. It had a thicker atmosphere. It had a period, early in the solar system's history, during which the conditions required for the emergence of biology were broadly similar to those on early Earth. If life emerged on Mars, and if dormant spores or chemically active biomarkers could survive interplanetary transport and re-entry, and the physics does not foreclose this possibility, then an uncontrolled breach of sample containment constitutes a contamination event with no historical precedent. So we build the quarantine. We spend conservatively hundreds of millions of additional dollars constructing a facility to contain what we paid tens of billions to retrieve. The terminal irony is precise and should be stated without embellishment. We are proposing to spend approximately $10 billion to break the natural quarantine that 56 million kilometers of vacuum has maintained between Earth's biosphere and whatever chemistry Mars currently possesses, and then immediately reconstruct an artificial quarantine at enormous additional cost to contain the results of having broken the first one. The solar system had a quarantine protocol. It was called distance. It was called vacuum. It was called the orbital mechanics that place Mars at minimum 54.6 million kilometers from Earth at closest approach. We are paying to override that protocol, and our first act upon successfully overriding it will be to build a more expensive version of it in a building in the continental United States. This is not a logical inconsistency. The scientific rationale for proceeding is coherent. The precaution is proportionate to the potential consequence. But as a statement about the nature of what we are doing, as a description of the fundamental character of this mission, it is clarifying. We are afraid of what we are trying to bring home. We are spending our civilization's resources to retrieve something we cannot safely interact with, cannot fully account for, and cannot reverse the decision of having collected. The tubes are sealed. The samples are inside. We do not know what the samples contain. We are spending $10 billion to find out. And we are building a prison to put the answer in. The universe has a preferred direction, and we have always known this, though we rarely say it plainly. Matter flows into gravity wells, not out of them. Energy disperses rather than concentrates. Entropy accumulates without refund or exception, and the entire history of our civilization's engagement with space exploration has been, in thermodynamic terms, an exercise in accelerating that dispersal by throwing our artifacts and our ambitions outward and downward, into the dark, into the wells, with no structural expectation that anything returns. We land on Mars because falling is cheap. We have not returned from Mars because climbing is expensive, and the mathematics of propulsion, governed not by opinion or budget cycles, but by the conserved quantities of momentum and energy that do not negotiate with legislative committees, dictate that the cost of returning even a trivial mass from the base of a gravity well to the top of it compounds faster than any civilization's economic capacity to absorb it, particularly when the civilization in question is operating on a finite energy budget derived from a single star, managing several simultaneous existential constraints, and being asked to justify the cost of interplanetary rock retrieval to a population that cannot fully perceive the 56 million kilometer distance between itself and the object in question. The Mars Sample Return mission is not a failure of ambition. It is an accurate display of where we actually are as a species, capable of extraordinary one-way gestures, capable of designing and building and launching and landing with genuine competence and genuine courage, but structurally, economically, thermodynamically constrained from completing the return leg of a journey we have been describing as a round trip for 60 years, because the return leg costs orders of magnitude more than the departure, and the departure already costs everything we can afford, and the universe does not offer discounts, refunds, or alternative thermodynamic pathways for civilizations that find the correct pathway inconvenient. Perseverance is still driving. The tubes are still waiting. The budget is still unresolved. The mission is still, in the precise language of its own independent review board, not executable. And somewhere in the rust-colored sediment of a crater that was once a lake, in tubes made of titanium and sealed with mechanisms designed to last decades if necessary, there are samples of a world that may or may not have hosted biology 3.5 billion years ago, waiting with the absolute patience of inanimate matter for a retrieval vehicle that may never come, because we are a species that is very good at sending things away from ourselves and has not yet demonstrated in any confirmed instance the capacity to bring the important things back. This is not tragedy. Tragedy requires an audience capable of perceiving the loss. This is physics. This is the Tsiolkovsky equation applied at civilizational scale. This is the one-way universe operating exactly as designed, indifferent to our plans, indifferent to our curiosity, indifferent to the 70-year-old question of whether we are alone in this solar system, a question that may already be answered in a sealed tube in a crater on a planet that has never given anything back and, by the mathematics of propulsion and the economics of a civilization that cannot afford its own ambitions, may never be asked to. The autopsy is complete. The patient was never alive.